We're gonna look at some problems, solve some problems concerning thermochemistry from the review document. I've got 27 of them highlighted, and that may not seem like a lot, but it takes a while to work each one. So since I finished the lecture last time we met, we've got 2 class periods that we can use to do this, and we can just run through half of them and then finish up on Tuesday and then go in the lab. And I posted everything that's been recorded so far. So you got the video from the lecture and you got the lab discussion we had. Yeah. Okay. Let's see how many of these I can flub. And with number 2. What's the kinetic energy of 1.56 kilogram object moving at 94 kilometers per hour? All right, so the question here is kinetic energy. What's the kinetic energy? Remember the formula for that is 1/2 mv squared. That should be in useful information too. The problem tells us that the mass is 1.56 kilograms and the velocity is 94 kilometers per hour. All right, you have to ask yourself, are these the right units to use this formula and give us the kinetic energy, which should be in joules? Okay, in order to end up with those units of measure for energy, these have to be in SI standard units. So mass is correct. It is in kilograms, but velocity is not. Velocity needs to be in meters per second. So that means we've got to do some conversions here. Remember, when you have a compound unit of measure, work on one of the elements at a time. So I'm going to do kilometers first. We need meters. So kilometers on the bottom, kilometers on the top, meters on the top is where we're headed. So for every 1 kilometer, we have 1,000 meters. Okay. That gets rid of kilometers, and now the distance unit is correct. Now we need to convert hours to seconds. And this means to be meters per second. Hours in the denominator, hours in the numerator. So how many seconds are there in an hour? 60 in a minute, 60 minutes in an hour. 60 times 60 is 3,600. Or you can stretch it, you can do 2 units here. Just convert to minutes first and then convert to hours. But I'm going to do it in one shot. So that leaves seconds on the bottom, gets rid of hours. So now we got the units of measure for our velocity. Just have to crunch some numbers. 94,000 and 3,600. And I get, my calculator says 26.11111 meters per second. Now, since all of these operations are multiply divide, I can keep that value until the very end and then settle on significant figures at the end. So what we would have here is we got 3 significant figures here, 3 here. So eventually we're going to end up with 3. The 1/2 on the outside, then mass is 1.56 kilograms. And then velocity is squared, 26.111. That's enough. Meters per second squared. So I've already got that one in my calculator. I'm going to square it while it's here. And then times 1.56 and divide by 2. So I get, let's see, I'm going to use standard notation. 531.7963 joules. Actually, the units that come out of this are kilogram meter squared per second squared. But that's equivalent to joules. Okay, so I can keep 3 of them, right? So I have to round this one off to 2. 532 joules. Should be up there somewhere. Wait a minute. Oh, kilojoules. They want the answer in kilojoules. Okay. That's joules. So kilo, if I put kilo here, that means this is 10 to the third. If I'm gonna put all of my information into this position of 1,000, that means I gotta move 1, 2, 3 to the left, right? 0.532 times 10 to the third kilojoules. So this would be kilo. I can cross that out. Now it's in kilo. And 5.32 times 10 to the first power kilojoules. Right. Excuse me, that's -1. I moved the wrong direction. Sorry. I moved this way. That's a minus. Okay. All right. We're just getting warmed up here. Yeah, thermochemistry is it's math intensive, unfortunately. Number 3. Which of the following statements correctly describes the signs of Q and W for the following exothermic process? P equals 1 atmosphere, T equals 370 K. All right, the process is gaseous water, water vapor going to liquid. This is the process that's being described. And they tell us it's exothermic. Is that correct? Yeah. If you go from a gas to a liquid, you got to give up heat because this is more energetic than the liquid is. Right? So it's exothermic. That means Q is a negative sign. Remember, everything is reference to the system. Whatever happens to the system, it's losing heat, so it's negative. We know that. Let's see, Q and W. How about W? If we're going from gaseous to liquid, look at it this way. If you have a cylinder here and you got a gas inside and it condenses into a liquid, but the pressure is constant. Pressure is constant in 1 atmosphere. Then what's going to happen? That gas is going to condense and leave a bunch of space in there. It's trying to make a vacuum. So this piston is going to move down, correct? Piston moves down to accommodate that loss of gas in the space when it condenses into this liquid. So that means for this system, pressure is being pushed down. So final pressure is less than initial, PF minus PI. This is smaller than that. So this is going to be a negative value right here. But work is minus P delta V. Oh, excuse me. Not P, V. Final volume is less than initial volume, which means this is a negative value, but that's a negative value. Right. W equals minus P delta V. We did that one 2 days ago. Okay. So a negative times a negative is positive. So W is going to be positive, and that makes sense. We're doing work on the gas because this is being pushed down. So we've got Q is negative, W is positive. And that would be C. Okay. We need to think about it in a minute. Okay. All right. I even have to stop and think about it myself. Because it's not really intuitive. I mean, I've been doing this for so long, and still there's an air of skepticism every time I do this. Number 7. One mole of an ideal gas is expanded from a volume of 1 liter to a volume of 8.93 liters against a constant external pressure of 1 atmosphere. How much work in joules is performed on the surroundings? Ignore significant figures for this problem. Okay. So, and it gives you a conversion factor. Maybe we'll need it, maybe we won't. Let's go back to the question. How much work is performed on the surroundings? Let's see if that's accurate. We've got a piston in here. It's under constant pressure, correct? 1 atmosphere pressure. Oh, yes. 1 atmosphere pressure, constant pressure. That's a constant pressure, okay? And an ideal gas is expanded from a volume of 1 liter. So this is, say, 1 liter to begin with equals initial volume. And then we're going to go this volume up to final volume of 8.93, what was it? Liter. This is the final volume. Okay. So how much work is being done? We don't even have to, they tell us work's being done on the surroundings, which is true, right? It's going from 1 liter to 8.93. It's expanding that way. So the gas is having to do work on the surroundings. But if we just use the formula, then we can answer that question ourselves. They told us, but they don't have to tell us. All right, so this formula is going to tell us minus P, 1 atmosphere, and delta V is final minus initial, 8.93 minus 1.00 liters. Okay, so that's 7.93 times 1, right? Positive 7.93 times a negative 7.93 liter atmospheres. There's a negative sign there. So our calculation confirms that work's being done on the surroundings. Work is being expelled by the system on the surroundings. That's that negative value. But that's the wrong units of measure. We need to convert it to joules. So we need a conversion factor that'll go liter atmospheres to joules. And the answer is 101.3 joules. 101.3 joules per liter atmosphere. .93 times. And I get, it's in standard notation. Okay, so I got a negative. 3 significant figures, 803. Oops. That was 0. 803 joules. And that would be B. Okay. All right. And we'll skip a few and go down to number 12. Okay, calculate the work associated with the compression of a gas from 121 liters to 80 liters at a constant pressure of 13.1 atmospheres. And the units measure in liter atmospheres, so we don't have to convert it to joules. So I like to draw a picture. It keeps me honest. We're compressing a gas from 121 to 80 liters. So we're starting off at 121.0 liters. This is an initial volume. And then it's going down to This is 80 liters, 80.0 liters. This is the final volume. Okay, and it's under constant pressure of 13.1 atmospheres. P equals 13.1 atmospheres. Okay, so we just plug it in the formula. Pressure, 13.1 atmospheres. Final minus initial, 80 minus 121.0 liters. Looks like we're going to get a positive value. Oops. There we go. And 13.1. So I get standard notation. Yeah, standard. Yeah, this is going to give us three significant figures, three significant, so we can keep three. 537 liter atmospheres. Okay. Okay, skip. Let's see, 14 through 17, these four are based upon that statement at the top. Let's see, 14, 15, 16, and 17. All right, what does it say? A gas in a 1 liter bulb at standard temperature and pressure is connected via a valve to another bulb that's evacuated. So we got a liter bulb here, 1 liter, and it's at standard temperature and pressure. So this is, standard temperature is 25 degrees C and pressure is 1 atmosphere. And then we're going through a valve to another one, and we don't know how big it is. Doesn't matter, it's a vacuum. Pressure equals 0. Okay. So I think we're probably going to open the valve. Yep. What occurs when you open the valve? And the first one is answer a question, what is true about the value of Q? What happens to Q? Second one, I'm going to put them all up here first. Second one is W. And we're talking about the sign. Looks like the answers are all related to the sign. Are they equal to 0, greater than 0, or less than 0? Or we don't know. This one's delta E, internal energy. And the last one is delta H. Okay. I'm going to take the easiest one first. This experiment is conducted at standard temperature and pressure. That means the temperature does not change. If the temperature doesn't change, there's been no heat transfer at all. No heat change. Right? So this one has to be 0. And if the pressure is constant, although I kind of doubt that, but we're sort of stuck. We're going to have to say that there's been no change in enthalpy either. Although there's a question there because pressure did change. But we're claiming that the pressure is not an issue. So we're saying that these are essentially equal. Now, how about work? Was there any work done? No, it's not pushing against anything. Like there was really, right? Remember, work equals force times distance. There's no force applied to anything traveling through a distance, so this one's equal to 0 also. And delta E equals the sum of work plus Q. Right? If they're both 0, then this one has to be 0 too. Okay. So what we're saying is that all of these terms are 0 under those conditions. Now that brings up another issue that we're going to get to. Let me see. Do we do that in this course? Take a quick look at our. No, second course. Why then is it spontaneously expanding into that space if none of these are greater than zero or less than zero for that matter? Right? There's another term that we're going to introduce next semester that explains what that is. I'll give you a hint. It's called entropy. Right. What we know so far does not explain that movement. All right, 18. Of energy, work, enthalpy. Oh, I've given the answer away because it's highlighted. How many are state functions? All right. Energy and enthalpy are state functions. And work and heat, Q and W, are path functions. It just means that state function is only concerned about what the state is. Where is it? It doesn't care how it got there. Or if you know where it was originally and where it is now, the path doesn't matter. These values are independent of the path. Whereas actual heat transfer and work done do depend on how it gets there. So C is the answer two. Two of those are state functions. All right, 19. Which of the following properties is or are intensive properties? Oh, okay, we're going to slip something from the past in on you. Okay, intensive properties. So we've got mass, and let's see, we have 5 of them. Yeah, we have 5. This is energy. This is concentration. This one is volume, and this is temperature. So how many of these are intensive properties? Does the value of mass change with the amount of substance? Yes, that's an extensive property. Temperature, does that change with the amount of substance? None. Doesn't. This is an intensive property. And in fact, the way we understand temperature is it's equal to the average kinetic energy of all particles in the substance. Volume, does that change with the amount? Yeah. As long as all the other factors are constant, volume will change. That's extensive. Concentration. Concentration is a ratio of one with 2 amounts. And this one is automatically intensive. Like grams per mole or moles per liter, things like that. Those values don't change with amount. Or density, mass per grams per cubic centimeter. Energy, does that change with amount? Yeah, this one is extensive. Okay, so we have 2 intensives, 2 and 4, which would be C. All right, 23. Consider the reaction. All right, we're going to burn some ethanol. Right, that's liquid with, yeah. And the equation appears to be balanced already. Make 2 CO2s and 3 water, correct? And the enthalpy for this reaction as written is negative 1.37 times 10 to the third kilojoules for these ratios. So this would be kilojoules per mole of ethanol or kilojoules per 3 moles of oxygen and so forth. Okay, so consider the following propositions. The reaction is endothermic, exothermic. The enthalpy term would be different if the water formed was gaseous. Which of the propositions is or are true? Okay, we didn't cover this in class. We covered the first possibility, endothermic or exothermic. And you can tell that from the sign. All right, this is exothermic. So that would be 2. This is exothermic. All right? It's negative relative to the system, which means it's giving up energy, giving up heat. The last one, the enthalpy term would be different if the water formed was gaseous. We're saying this is a liquid, this is a gas. Gas. The answer to that is yes. If water is given as a gas, it won't give up as much energy. Wait a minute. Let's look at it this way. The reaction takes place. There's so much heat there that this is initially water vapor. It's a gas. Right? We saw that. Didn't we see that with our tubes in the Bunsen burner? We had the water vapor condensed on the cold glass. Okay. So if it condenses to liquid from that gas, then it gives up a little more energy. Right? So if it goes from a gas to liquid in this process, then this should be, well, if it was still a gas, it'd be less than that because some of that energy would still be contained in the gas. But since the gas condensed to make this liquid, this is bigger than it would have been. Does that make sense? Yeah. Okay, so yes, 2 and 3 are both true. It will be different. Phases do matter when we're calculating or reporting enthalpy changes in a reaction. 24. Not simply due to the chemical changes, chemical reactions, but to the physical changes also. 24. How much heat is required to raise the temperature of 5.75 gram sample of iron from 25 to 79.8? Okay, this is simple. It's like a one-step problem. If we're trying to determine the amount of heat that's needed to raise the temperature of this iron, we're talking about Q equals something, right? Specific heat value for that iron times its mass times its change in temperature. That's the formula. Okay, so Q is going to be 0.450. 0.450 joules per gram degree C. And then the mass is it in grams? Yep, 5.75 grams. All right, so we've taken out this term right here. All right, these grams are gone. Now we've got joules per degree C. We need a change in temperature. So what's the final temperature? 79.8, right? 79.8 degrees C is final temperature. minus initial temperature, 25 degrees C. Okay, there's our formula. So let's see. I'm going to do that PEMDAS, parentheses first. 79.8 and 25 minus. And I get 54.8. So this term right here is 54.8, and that's right. Line up the decimals. You can keep that decimal, so that means this is change in temperature, and that cancels temperatures. Now that times 5.75 and times 0.450. So I can keep three significant figures. Let's see. Is it in standard notation? Yep. 142 joules. And that's a positive. So that means we're adding energy to the iron. The iron is our system. Okay? Nick, 26. $32.5 gram piece of aluminum, and its molar heated capacity is given. Heated to 82.4 degrees and dropped into a calorimeter containing water with a specific heat of 4.18. Oh, they left off the last one. 4.184. We'll use what they've got because it may affect the outcome. Initially at 22.3 degrees. Final temperature of the water is 24.2 degrees. Ignoring significant figures, calculate the mass of water in the calorimeter. Okay, so let's see what we've got here. 32.5 gram piece of aluminum. So mass of aluminum equals 32.5 grams. Okay, and we're heating that aluminum to, well, let's go ahead and put the specific heat of aluminum. We got that. 24.03, 24.03 joules per mole degrees C, right? Molar heat capacity. And the temperature is 82.4 degrees. Temperature of the aluminum is 82.4 degrees C. So far, so good. So we're going to put it in a calorimeter with water. The mass of the water is unknown. That's the question. Right? Calculate the mass of the water. 4.18 is the specific heat of the water. 4.18 joules per gram degrees C. And its initial temperature of the water, let's see, initial temperature of the water is what? 22.3 degrees. And the final temperature of the water is 24.2. There we go. So that's all the information that's contained in the problem. Where do we go from here? If we're in a calorimeter, calorimeters are by nature isolated systems. Nothing goes in or out. Mass, no heat, none of that. So if this is all in the calorimeter, everything that happens in Vegas stays in Vegas. Everything, all the heat terms are equal to 0. We're not given information about the calorimeter, so we have to just ignore it. So this is going to be the heat term for the water plus the heat term for the aluminum. Right, then we expand it from there. Okay, so I'm going to move this over as close as I can get. 0 equals heat term for water. So that's, okay, I'll be thorough. This term is specific heat of water. Let's see, yeah, that's right. Mass of the water, which is going to be our unknown. And then the change in temperature for the water. Right? And then we add to that the specific heat of the aluminum plus the mass. We can't do that. We don't know what the specific heat in terms of mass is. This is molar specific heat. So this has to be not mass, but moles of aluminum, simply because of the units that are given to us. And then the change in temperature for aluminum. All right, so we've got a conversion to do. We've got to change this to moles. So I don't want to mess with that. So let's put it over here. 32.5 grams of aluminum. We want to convert it to moles. So we need molar mass, right? 2698 for aluminum. So we divide 26.98 into 32.5. And that's 1.205. 1.205 moles of aluminum. Now we can move. Okay, so let's fill in what we know. Specific heat of water. Okay, this is going to be one term. Specific heat of water is 4.18. Okay, I'm going to leave out the units simply because there's not a whole lot of room. Mass of water is unknown. Change in temperature. Final minus initial. What's the final temperature of the water? 24.2. And the initial is 22.3 degrees C. That's the first term. You have to be real methodical about this, because if you get these things reversed, then you're going to end up with the wrong answer. Okay, specific heat of aluminum is 24.03 joules per mole degree C, and the moles 1.205. And then the temperature change. What's the final temperature of the aluminum? Same as the water. It's come to equilibrium. So the water and the aluminum are the same temperature. So it's 24.2 minus its initial temperature, which is 82.4. There we go. Now it's all set up. We just have to solve for that unknown right there. This is all numbers, so we can reduce this to some value. Right? So I'm going to do 24.2 and subtract 82.4, negative 58.2, and then 1.205 times that, and 24.03 times that. So this part is minus 1685.25. Now, what's our value there? Well, the temperature canceled out, moles canceled out, so this is joules. That is joules. Okay, how about this one? This one we can get a factor here, and then we have this unknown attached to it. 24.2 and 22.3 minus times 4.18 times, and this term now is 7.942 mass of the water equals 0. Okay. So what we need to do is get all the numbers on one side and all the unknown calculators on the other side. So this one would be a negative. On this side, it'd be a positive, correct? Okay, so I'm gonna flip it around and put this over here, 7.942 M water equals a positive 1685.25. So now all we have to do is divide this one by that one. Let's see. Yep. Changed. So I get how many significant figures? Looks like 3. 212 grams. Okay. This is the best way to solve a calorimeter problem. But it does require that you're very methodical about the input of your values and your calculations. If there's any Achilles heel in this procedure, it's that. You can't go at it too fast or without stopping periodically and thinking. Be sure you're on the right path. All right. So the one time I did stop in here was to recognize that the specific heat factor for aluminum was in terms of moles, not grams. That required a separate calculation. $27. I'm gonna start to get a little weak. I've got some old ones in here turned upside down. Maybe it'll work for a little while longer. Let's see. 45.9 gram sample of a metal is heated to 95.2 degrees, placed in a calorimeter with 120 grams of water at 21.6 degrees. The final temperature of the water is 24.5. Which metal was used? Okay. The variable there is a little c. It's the same as S. That's specific heat. I think the reason they use little c is because big C is the heat capacity. And little c is specific heat capacity. This is heat capacity is actually heat capacity is an extensive property. If your calorimeter is bigger, it's going to have a greater heat capacity. So a specific heat capacity turns that into an intensive factor because it's ratio to mass or moles. I think that's why they use little c, but we've been using S, so we're going to stick with S, specific heat capacity. All right, let's see. So if we're going to figure out which metal it is, we need to, our unknown is going to be the specific heat of the metal. So let's see, what do we have? 45.9 gram sample of metal. So mass of the metal is 45.9 grams, right? Yeah. And its initial temperature is 95.2 degrees. Okay. What's its final temperature? Final temperature of the water, 24.5 degrees. And its specific heat is our unknown. Then we have water, mass of the water, which is 120 grams. Okay. Initial temperature of the water is 20, that's final, 21.6. Final temperature of the water is the same as the metal. And the specific heat, probably using the same value, 4.18. Yeah, 4.18. Joule per gram degree C. Okay, that clock's starting to go already. We have another one. Okay, so we set it up the same way, right? 0 equals the Q for the metal plus the Q for the water. And then the Q for the metal would be specific heat of the metal, which we don't know, times the mass of the metal, 45.9 grams, times change in temperature, which would be final 24.5 minus 95.2. Okay. Then we do the water term. And it's going to have everything included. 4.184. Oops. I got to remember they chopped off the 4, so I'm going to do that too. And then times the mass of the water, 120. 120.0 grams. And then the change in temperature of the water is final 24.5 minus 21.6. There we go. So now we're solving for that unknown. Okay, let's do that final term down there. What'd you get?
For that one?
Yeah.
Or 2.9.
What?
Right? Well, I haven't multiplied yet. I'm just, that's the.
Okay.
The change in temperature.
Okay. Times 120 times 4.18.
1454.64.
Yep. 0.64. That would be joules. Okay. And plus this one, so we need a change in temperature there.
70.7 negative.
And then times 45.9.
32.513.
Yep. So this is negative 3,245.13 times that value. Okay. So let's just bring this one over on that side and make it positive, and then we'll be hunky dory. CM equals 1454.64, and then SM is this one divided by that one. And I get 0.448 joule per gram degree C. Closest one, iron. That one's getting weak too. All right. $28. See what 28 has to offer. The only reason I'm working these out in detail is because we have time. If I get rushed, then I just set them up and let them go. $28, I said? Yeah, 28. Okay, you take 295.5 grams of a solid at 30 degrees, let it melt in 425 grams of water. The water temperature decreased from 85.1 to 30. Calculate the heat of fusion of this solid. Okay. That sounds like it's a huge problem. But when we break it down and put what we know on the board and then think about what the formula would look like, it's not so bad. The solid is 295.5. So the mass of the solid equals 295.5 grams. right? And it is at 30 degrees C. So its initial temperature is at 30 degrees. Okay. The mass of the water is 425 grams. So the mass of the water is 425 grams. And the water temperature goes from 85.1 to 30. So the temperature initial of the water is 85 point, what did I say? 1 degrees C. And its final temperature is equal to 30, right? Yeah, 30. Okay. Oh, so the temperature of the solid didn't change. Temperature of the solid did not change. All right. You know what that tells me is that we don't even need a solid term in the when we determine the amount of heat that was given up by the water. Right, the water went from 85 to 30, so it had to give up energy, and that energy went into dissolving that solid. Melting that solid. Heat of fusion is a measure of the amount of heat for a solid to change into a liquid. If this MS goes to ML, then we have a delta H of fusion, that value. Okay, so really all we need to do, since this temperature didn't change, what we need to do is find out how much heat this represents. And they didn't give us the S for water, but we remember what it is. 4.18 joules per gram degrees C. All right, so really all we have to do is say, what's the Q for this water? How much energy did it give up? It went from 85 to 30. So let's see, S is 4.18 grams per joules per gram degree, and then mass is 425, and then change in temperature is final minus initial, 30 minus 85.1. Okay, so Q is what? All right, that's minus 55.1 degrees, 425 grams, and 4.18 joules per gram degree. All right. So this is minus, I'm going to use scientific notation, 7,885 times 10 to the 4th joules. And the value, the answers are in joules per gram. Okay. This is the amount of heat that was given up by the water. Where did it go? Well, if this is the system where it is negative, the water gave up this heat and it came over here as a positive value. So that's why we don't have a negative sign on that, because the heat of fusion is positive. In other words, this amount of material absorbed that heat, which makes it positive. Okay, so we just take this value plus 9.7885 times 10 to the 4th joules and divide by the number of grams. Joules per gram will give us the heat of fusion. And we're in standard notation. So I see I need to move that decimal over. This has got 4 significant figures in it. 331.3 joules per gram. So C is the closest one to that. They actually threw away a decimal. Let's see, 32. Now think about that procedure. What's the other thing that's required in order to determine the heat of fusion for that substance? It cannot be soluble in water. If it's soluble in water, then you've added another factor, right? The heat of solution. Okay. As long as it's insoluble in water, we're good. All right, 32. It's kind of like trying to determine the volume of an irregularly shaped solid. Well, let's see. Normally you put it in water and measure the volume before and the measure volume after, right? But what if that solid is a chunk of potassium? You have problems. Okay. All right. In the lab, you mix two solutions. Each one is at the same temperature, and the temperature of the resulting solution decreases. Which of the following is true? If you mix those two together, two solutions, you mix these two solutions together, right? And let's see, they both go into a container. And the temperature at the same temperature. So initially, this is equal to that, the same temperature. And the final temperature is what? Decreases. Final temperature is less than the initial temperature, right? So where did that heat go? We can't create or destroy it. So if it had a certain amount of heat here and the temperature decreased, the heat had to go into the reaction. We lost energy from the system in order to do that. Now, if we're talking about the solution itself. All right, which of the following is true? The chemical reaction is releasing energy. No, it's absorbing energy. This is an endothermic process. The endothermic process. So A is not it. The energy release is equal to S times M times delta T. Well, it may be S times M times delta T, but it's not released. It's absorbed, right? Got to pay attention to the wording, right? So B is false. Let's see. A, B, C, D, and E. Yeah. So these two are false. C says the chemical reaction is absorbing energy. Indeed it is. The chemical reaction is exothermic. No, it's not. It's endothermic. And E, of course, has to be false. More than one of these is true. No. Only one of them is true. That one. Now, when we get to the point where we can do our calorimetry lab, which is down the road, we're going to set it up, this reaction, so that we can talk about it in these terms. Right? Overall, we're inside the calorimeter. We're going to introduce a term for the calorimeter. Right? So we can account for any heat that's absorbed or given up by the calorimeter. Then we're going to have the heat for the water, because the process is going to be taking place in the water where we're dissolving a solid. Right? So the heat change in the water. And the last term is the Q of the reaction. The heat that is assigned to the dissolution process. That's the term we're going to be looking for right there. Okay. Just giving you a taste. We'll talk about it more when the time approaches. All right, 36. Beck, you're curious. I'm sure there's a video on it already in Brightspace. 36. Exactly 123.7 joules will raise the temperature of 10 grams of a metal from 25 to 60 degrees. What's specific heat? Actually, our problems are getting simpler. If we're looking for the specific heat, then we can use this formula, S M delta T. We just solve for the specific heat, right? So it's Q over M times delta T. So the amount of energy is 5 kilojoules. All right, that's the wrong unit of measure because this is going to be in joules. So 5 kilojoules would be times 10 to the third joules. Let's see, what's the mass? Oh, heat turn. Wait a minute. I put the wrong value in there, didn't I? Yeah, 123.7. I'm looking at the wrong one. I'm looking at 35. Scratch that. Let's put in the correct values this time. How about it? 123.7 joules. There we go. Then the mass, which is 10 grams. And then the change in temperature. From 25 to 60. 60 is final. Minus 25 initial degrees C. Okay. That's fairly straightforward. That's 35 degrees, isn't it? So I get 0.353 joules per gram degree C. All right. Scroll. Let's see how we're doing. 38. This might be a good place to stop then, because that'll give us enough to do on Tuesday. Right?